Sylvain, I would now actually invite you to please start your presentation. So before starting, I would just formally like to introduce Professor Sylvain. Professor Guilley has been working in hardware security for the longest time I actually know. He was one of my supervisors back in the days, so like I know him since about 12 years now, and he starting from working as a researcher in hardware security. Now Silva is actually working as part of Secure IC company where he's working as a director and basically providing state-of-the-art solutions to different problems and to actually different domains to come up with more secure products and stronger evaluation. So without taking much time, I would like to pass you the mic. I think I'm muted. It's unmuted.
Okay, thank you very much. Am I audible now?
Yes.
Okay. So thank you very much, Shivam, for this kind introduction. Thank you, Shivam and Avi, for giving me this opportunity to present very recent results about application of machine learning to security topics. Actually, this presentation will be about the discovery of a hardware Trojan in chips. Okay. So let's get started. Just a few words of introduction. This work is actually a collaboration with colleagues from Japan, from NTT Secure Platform Laboratories. And the experiments were carried out on both sites. And so we are very happy actually to already got awarded a best paper prize for this work at the ICS conference. And I now present to you an updated version of those results. Here is the outline of this introduction, of this presentation. So first of all, a general introduction about hardware Trojans. So it's my great honor to open the workshop. So I need to introduce a few definitions and concepts. All right. Then I'll come to the contributions, which are mostly a very improved way to do the Trojan detection in conditions which are realistic. Meaning, as I shall detail, the Trojan is very stealth. It's not activated because we have no clue that there is a Trojan in the chip. And the only way actually to detect the Trojan is to characterize chips which are supposed to be genuine, okay? But the attacker cannot train on both, let's say vanilla chips and infected chips. The assessor only has at his disposal vanilla chips, okay? I'll explain the experimental setup and the machine learning algorithms we ran and how they perform well with only something like 20 repetitions of some demo code within the chip, which is sufficient to acquire data to recognize whether the chip is genuine or has been somehow modified. Okay, so general introduction. So today, that's the way it is. We design the chips in one country, then we will go for production in another country, and assembly will also be done in even a third country, because this value chain is segmented, and because the plans, the know-how, the people are located on different places. So this means that the journey of a chip is quite long, and the attack surface, so any party willing to disrupt the chip security can be distributed around the planet. And so we have a real concern that some modifications, malicious modifications might be done. So this is our context and our hypothesis that this will indeed happen, okay? The modification can be, as I shall detail, anything from changing the firmware to actually even modifying the layout and changing the gates so that the hardware is actually so permanently modified. Okay. There are a lot of threats, as I mentioned in this slide, about counterfeiting, overproduction, and even reverse engineering. All of those are very serious because they affect the trust in the products. So they clearly need to be addressed somehow by some countermeasures. So in this talk, I focus on the hardware Trojan, which is probably the worst situation, because actually not only we have chips which we don't control the dissemination, but also those chips contain a backdoor, which can lead to, for instance, data exfiltration, for instance, taking the control remotely of the chip for whatever reason, okay, most of the time for pretty bad reasons, as you can imagine. So let us be specific. Hardware Trojans are malicious modifications of the chips. Usually we say they have two parts. One part which is actually the trigger, which is the logic which activates the Trojan, and then some logic for the action of the payload on the host chip, which we call so we have the trigger, and then we have the payload part of the Trojan. Okay. So the payload can do anything from just DOS to degrading the performances and even changing the behavior to leaking information without the user being able to notice anything. You see, so different impact, and some impact which can be completely critical. So this is a representation about the design flow for an IC and actually a PCB. So many steps, as you can see on the left, involving so some design inputs, is involving some tools, involving some third-party IP. So this flow actually is distributed. Many actors, many different people are involved, right? And so the attack can be anywhere. So on the right, we can see actually that the attack surface is extremely varied because you can imagine a lot of different scenarios. So clearly, we try to limit the risk by working on each element in the chain to make it trustworthy, like to do equivalence checking, to simulate, verify. That's something important. But in the end, there is another way to consider the security. So the other way is to say, okay, somehow I caught a Trojan, and now I have my final product. Let me check my final product whether or not at some point, I don't know where, okay, but at some point it got infected by a hardware Trojan. So let's try and characterize and decide whether yes or no this chip has been modified, you see. This approach is required because there are also so many different ways to implement a Trojan. So there has been a lot of attempts to pigeonhole a Trojan into different categories. There is on this slide a very considered classification of the Trojans, depending when they are inserted, so early or late in the design flow, whether the system is targeting the low levels of the chip, or actually whether it resides in the software stack, you see. So by the way, the Trojans I will be showing to you is something mixed because it contains one part, actually the payload is in hardware, but actually the trigger is carried out by software, you see. So this kind of Trojan, you cannot detect it and understand it fully by analyzing only so the masks or the silicon chip, but you also need to analyze the firmware, which will be injected later on into the product. And so in our use case, actually, the software can even be implemented as a kind of virus, you see, after the hardware platform is already deployed in the field, you see. So this classification is kind of relevant because it shows the very large variety of different Trojans you can have in the field. Huh? Then just quickly to comment on this slide, you have also you can classify the Trojan depending the way they are activated. Some Trojans are always on, but some Trojans are triggered. Okay, so this gives some hints also for the detection. Okay, so in our use case, we will consider that the Trojan is triggered, but actually we will be detecting that it is sitting in the chip, even though it is not actually triggered. Okay, because the triggering of the Trojan is usually very stealthy, and activation will be done only in a selected time by the attacker, okay? And so it's not that realistic to assume we can catch the Trojan while it is waking up, all right? And just to finish about this classification, so the Trojan can also be classified according to its effect. So the kind of action it will have on the host chip and the host system, according to where it is located. Some of the Trojans are in the I/O because they want to exfiltrate information, but some of them are in very general purpose part of the chips, like the processor or the memory, which is our target actually, and where it's much more difficult to identify them because actually there is no clue what kind of modification can be done there. It's completely so yeah, general purpose logic. So that's the case we consider here. Okay, and then of course physical characteristics. The harder Trojans to detect are those which are extremely small in size in terms of the footprint. Okay. So Trojans are out in the field. You've been hearing most of those news because they were actually published and so the media got a lot of traction on that. There was this China versus US spying, you know, on the on some of the chips used in the USA. Then the Snowden also talking about different things for Cisco, etc. So those have been reported. It's public information, you see. I don't. It's not now the correct place to discuss about exactly what was done, but it's just to show a track record about a few hardware Trojans as they were discussed. So this topic is available for so general audience, and those days we need to understand how to increase the trustworthiness of the chips, and so to raise awareness and also to have a systematic way to screen the chips, we need to develop some tools and techniques, and that's exactly the topic of my talk. Okay. So how to protect? Clearly, the best is to prevent. Okay, I'm not going to go into those details because it's a, you know, there are many techniques. Hopefully, simply by checking the quality of the design chain already, which is done, by the way, in many frameworks. If you go for security certification of your chip, you will have strong requirements on the way the chip is designed and who is doing what, and this is checked. Okay. There are also some supportive methods. This means some additional logic, additional software, okay, which is there to actually check that everything is occurring in a nominal way when the chip is actually working. Okay, but another philosophy, and which is the one I now consider, is that okay, we cannot completely exclude that the chip will be clean. That so maybe it will not be clean. Okay, so we want to detect either pre-silicon or post-silicon. And actually, the best is to detect post-silicon because we are at the end of the complete design flow, and we'd like to make the detection non-destructive, because if we see that the chip is clean, then we want this chip to be used for its purpose. Okay, so because clearly detecting a chip with modifications of the chip is nice to show that indeed there has been a modification, but then if there was no modification, of course we lose the chip. Okay, so now let's go for the contributions. So we will go for non-invasive methods to detect hardware Trojans in the chips, okay, using side channel methods. As you know, side channel analysis is a field which got a lot of attention and which is very mature. So you can find some platforms to do side channel acquisition, which are available off the shelf. So in this work, actually, we used the analyzer from SecureIC, but actually the only requirement for the experiments is to be able to observe some EM electromagnetic emanation from the chip, and that will be the traces we need actually to make the binary classification. So genuine versus Trojan. Okay. Clearly, there are already some existing works. I want to give them some credit there. Okay. So what is specific to our work? Again, I just repeat, we go for very stealthy Trojans. The impact on the silicon area will be something between 0.5 and 0.1% of the total area. We go for a Trojan which is hidden into a RISC-V CPU. So it has nothing particular to disrupt, you see. So imagine, for instance, a Trojan in a RAM. You see the geometry of the RAM will be changed in a visible way because it is highly structured, whereas a processor is usually synthesized into a gate of a sea of gates. Okay, and so a few more gates from there to there is not going to be that much visible. Okay. And we really want to have a detection rate which is pretty high, close to 100%. And most importantly, we want to have as little as possible false positives, because you see, at the end of the day, we want to be able not only to screen 100 or 1,000 chips, but we want to go for an automated method which can be done at the tester stage while in production. So in a plant where typically millions of chips are produced every day, all right? So the test methods must be fully automated, and if we have so very low false positive, that's very good, because it means that we will reduce the work to cross-check that actually the chip is indeed sane or not. Or we will actually, you see, improve the yield, because maybe the decision, if we have a suspicion of a hardware Trojan, will be to just throw in the trash this part. But in this case, we really want to avoid that, because the yield of the fabrication needs to be as high as possible, for the chip business to be profitable. Huh? Okay. So actually, we go for almost 100% detection rate and 0% false positives. That's actually the real goal we want to reach. Otherwise, the methodology will not be deployable in an industrial context, you see. Okay, so let's go. We have two boards. We will be implementing the Trojan into a Pico RV32 and a Freedom E300 from Sci-Fi. Okay. The Trojan will be in the logic of FPGAs, and you can see the two platforms here. So we wanted to use at least two different setups to prove that our methodology is not specific to a given hardware. All right. Then also, for the sake of being representative, we inserted three different kinds of Trojan. All the three of them are software-enabled hardware Trojans. And they are designed actually so that the regular software which runs on a regular chip, so without the Trojan, will behave nominally, okay? And only when this software, so the same software, is running on the Trojan chips, it will activate the backdoor. Okay, so actually we leverage some one instruction, which is the division. Specifically, you know, we checked actually the code which is emitted by a compiler, GCC or LLVM, and the way it uses the div instruction. And typically, when we divide by 1, so it has it has no impact on the functionality of the software. Okay, it's idempotent instruction. Okay, I divide the register by 1. Okay, so there's no modification. All right, and this code normally shouldn't appear when I compile whatever off-the-shelf code, my OS, my application. It should never appear, you see. And so this will be added by the attacker, and that will be the trigger. Okay, so it's a software trigger. All right. And next, so the payload for the Trojans 1 and 2 is actually to copy one register into the program counter so that actually we can jump anywhere. All right, this is arbitrary, so taking control of the platform. And for the Trojan 3, we actually change the privilege of the RISC-V. And because of that, just changing the privilege is just flipping 1 bit. So we get a Trojan which is very small in hardware, you see. And so in this chart, you can see the overhead of the 3 Trojans, which is extremely limited. And so you don't expect to see something visible when doing visual inspection of the chip. That's the idea. So to show you some idea how stealthy the Trojan can be, here you have the floor plan of the genuine design, and in the right, actually, this is the modification which is carried out by the attacker while inserting the Trojan. And you see only a few, ALM, meaning the logic gates are changed. So here it's FPGA based. So actually it is the configuration which is a change, not really the hardware, you see, but it's a very good simulation of what an attacker would do in ASIC. Okay, and so here we complete white box Trojan, because we know we have the 2 designs, and so we can compare them, right? Then we need to now I am the assessor, so I want to decide whether or not this Trojan is there, even though it will be sleeping in our experiments. Okay, we don't activate the Trojan, so we use this analyzer platform with EM probes, which will be moved using XY table over the chip. Okay. And we capture some traces. Each trace will consist in 5,000 time samples. So we run whatever software actually. It is doing NOP and doing some incrementation of the accumulator. Okay, just a demo program, because actually we have no clue how to trigger the Trojan. Okay. And we will be repeating the measurements n times. And the cartography will consist in moving the probe X and Y. So in this case, at 13 positions X and 13 position Y, resulting in 169 different traces. So you see, you can visualize that as a matrix, as you can see in the graph. And this matrix is something which we can feed into some either statistical tools or machine learning algorithms. Okay, so let's see for the detection. First of all, I want to give you a feeling about the difficulty to detect the Trojan. So let's compare visually two traces, one acquired from an FPGA which doesn't have, and then an FPGA which has the Trojan implemented. And we select amongst the 5,000 time samples, we select only one, which is the one with the most variability. And actually, so there's absolutely no way to detect that something is strange. You see the amplitude is also varying across the chip, but that's not due to the Trojan. That's just because we have some clock generator, you see, or which is actually generating some EM signal, but it's not related to the hardware Trojan. Okay, so this means that actually we really need to detect something which does not, stand out clearly in the traces. Okay, so actually what we will be doing is to repeat the measurements. So actually we will be scanning the chips, the FPGA surface, not only once, but actually n times. So in this case, 20 times. Okay, and so we check as we grow our number of traces, so our matrix, okay, the size of our data, so the campaign, we will be checking how we manage to improve the accuracy of detection and the false positives. So in the first place, we use a state-of-the-art t-test, and which is a tool, a generic tool, which is meant usually to detect the deviations between two populations in terms of their mean. But this method, yeah, it works actually, but you see the accuracy is really bad. We don't want to detect with a probability of 60 or 70%. It's clearly not enough. We want to reach 100%. And regarding the false positives, they are really too high. 30% of false positives. It really means that the method will require other inspection techniques, and that's not viable from an industrial process point of view. Okay, so we want to do something better, and actually we go for machine learning. All right. So actually, I will discuss two methods. So first method is to use supervised machine learning, and second method to use a combination of semi-supervised and t-test. The second method does not require the golden model. Okay, so it really means that it can be applied in production, even though we have no clue what the Trojan will be, which is the case in general. So first of all, the method one, we now go for different machine learning algorithms. So SVM, multi-layer perceptron, decision tree, and K nearest neighbor classification. All right. So we have a first stage where we need to train. Right, so we use 80% of our acquired data for this purpose, and then 20% for checking. Right, so we already have some very nice results. So see, for instance, for the SVM, for the Trojan 2, we reach 100%, okay, which is our goal. But actually, we fail to detect with high accuracy some of the Trojans. Okay, so this is positive, but not fully satisfactory because we want to do something which is better. Also, you see here in terms of the false positive, for the hardware Trojan 2, we have no false positives, but we have something which is still too high for Trojan 1 and 3. Okay, so those are the first results. Now the good news, and actually the key takeaway of my presentation, is that we went into another setup using outlier and novelty detection methods. Here what we do is that we only train on a chip which we take as a reference. And we have no idea actually when we train that some chips will contain or not the Trojan. So we train only on a batch. So say the chips resulting from one wafer. Okay, so they are most likely all the same, and so we will take them as the reference. And then we will be checking other chips, and so we want to decide whether they contain something which is strange. Okay, like we will say those chips are outliers, so their EM emanation differs. Okay, so this is a clue that something has been changed. Or a novelty detection methods. So novelty meaning that it's something we've never seen before, and also this is a hint about some stealthy malicious modification. All right. So we use 4 different algorithms just for the sake of validating the method and choosing for the good, the appropriate so machine learning algorithm. So we have the one class SVM, elliptical envelope, isolation forest, and the local outlier factor. Okay, from the genuine data set, we use half of it for the training, and then actually we will be using a mix. So genuine design and the design with the Trojan, hardware Trojan, for the validation. And so that's how we do it. Just to mention that we have a pre-processing on the data, which consists in computing the t-test of our input data. Okay, so that's the only pre-processing we do. We don't do any manual processing or feature extraction apart from this t-test. Okay, and those are the results we get. You see that mostly we reach the 100%, and for the detection rate, and the false positive rate also collapses to 0 when we have as little as 20 repetition of the measurements. So we reach the goal with elliptic envelope and with local outlier factor, as you can see here. And we are happy with this method, and we can now deploy it at the industrial scale. So just for comparison with the state of the art, you can see that we significantly improved actually. So we really wanted to have this 100% target, and so we got it. Okay, so conclusion, detection of the hardware Trojan is still a vivid topic. So we are pushing now to have a detection which is not ambiguous. Okay, the good news actually from this study is that not only we get rid of the need to have some chips with the Trojan to learn their behavior. So we don't need that. We only need a batch of chips from one wafer. Okay, so I say sane, but actually they can also be already Trojan, because actually the methodology will be to detect that there are some modifications in another wafer. Okay, So that's the first point, and the second point is that so we want this figure of 100%. Okay, so and we achieved that. Let me maybe now stop and welcome some questions. Okay, thank you.
Thank you, Sylvain, for the very nice talk. We have some questions lined up actually for you from the audience. I'll just read them out, and you please are free to answer them. So the first one from Henry is that on slide 19 you use EM measurements, and so in that case, does the processor works on the same measurements or same input, or does it use random inputs?
Yeah, it's a good point. So actually, we were running one software. We didn't really study which software will lead to the best detection. So actually, as I mentioned, it's just a sequence of NOP and incrementation of the accumulator. So very basic. Probably, actually, we can improve the detection rate by using a code with more numerous instructions, but that was not something we studied. So it's a way to improve actually the detection probably. So as a future work.
So we have now a two-part question from Akash Patil. So his first question is that what is the assumption if the attack is done by the design engineer who is introducing Trojan into the PNR, or is it the cat tool which is inserting the
Yeah. We have actually two different situations. So one situation is that the modification is on the layout after the place and route phase, and we have another assumption that the Trojan is actually in the source code of the RISC-V, okay, at RTL. Now we make no assumption whether this was done manually or by a tool. So what matters for us is just the resulting design, which is modified.
So the second question again from Akash is that does the method change if you change the Trojan, or the method is uniform across any type of Trojan?
So Shivam, I had some difficulty to understand the question.
So the question states is the detection method Trojan aware, or does it change if the type of Trojan changes? Like if for HT1, HT2, and HT3, does the method remains the same, or does the detection method changes?
Okay, got it. No. So the method is completely agnostic with respect to the Trojan. Different Trojans for the sake of the validation of the methodology.
I have one final question from David, who is asking if the technique can be extended to a non-supervised setting when the golden model is not available.
Thank you, Debapriya, for the question. So actually, the methods we used are semi-supervised, but being completely so non-supervised. Why not? Why not? So my guess is that we need still some training to have to have a good classification probability, and it's, so to say, it is free, yeah, because after production I have some engineering samples and I can train on them. But it's a nice it's a nice idea. It's a nice idea. So currently we are satisfied from the applicability of the method to use semi-supervised, but no, it's a nice avenue for future research.
I also have one small question, Sylvain, which is also like kind of related to the topic of this workshop. So basically, what we saw in your work that you were able to get very nice results by using quite simple but well-studied machine learning algorithms. So do you see, like, if we like the possibility of using more complex algorithms, will they help, and or like in terms of scalability or detection rate? For example, use CNN or like the more recent algorithms which are developed in the recent days.
Shivam, you're definitely right. Clearly here, those results are a proof of concept, and clearly we can go for testing more machine learning techniques. My hardware Trojan is a vivid topic, and there is some margin for improvement, and also let's go for mature solutions with 100% detection rate, and so I want to encourage more research. So actually the goal eventually is that all the the work on side channel analysis can be used constructively for the sake of screening the chips against hardware Trojan. So clearly this is very trendy, this is feasible, it is something realistic, and so let's encourage more work. So yes, thank you for your suggestion, and so let's have the community work in this direction. And by the way, I just want to acknowledge the Secure project, for studying so this topic, and actually so tending to achieve those goals.
Thanks, Sylvain. Thank you for the wonderful talk. So, with the interest of time, I would actually now invite Stefan to share his screen.